Okay, today let's tackle section 2.1, relations and functions. An ordered pair is a pair of coordinates written in the form xy with parentheses used to locate any point on a coordinate plane. You can graph ordered pairs on a coordinate system with two axes. Remember that each point in the coordinate plane can be named by exactly one ordered pair and that every ordered pair names exactly one point, so they're unique. Cartesian coordinate plane is a plane divided into four coordinate quadrants by the intersection of the x-axis and y-axis at the origin. The x-axis is the horizontal number line, which is side to side. The y-axis is the vertical number line, that's the up and down one. The origin is 0, 0, and the quadrants are the four regions into which the x and y axes separate the coordinate plane. So here's our Cartesian coordinate plane, the x-axis, the y-axis, the origin, and the quadrants, 1, 2, 3, 4. They should make a C, as in Cartesian Coordinate System. All right. So a relation is a set of ordered pairs. The domain is the set of all x coordinates of a relation, and the range is the set of all y coordinates of a relation. So if you have trouble remembering which one is the domain and which one is the range, then remember D alphabetically comes before R, X alphabetically comes before Y. So they go in alphabetical order. So hopefully that'll help. A function is a relation in which each element of the domain is paired with exactly one element of the range. And this is important. It just means that one x is paired with exactly one y. Okay? Mapping we'll show you in just a second. It's a nice visual way to show each member of the domain is paired with each member of the range. And a one-to-one function is a special kind of function where each element of the domain is paired with exactly one element of the range, and each element of the range is paired with exactly one element of the domain. So let's do some examples. Up here we have some mapping. A mapping is basically some ovals that we've drawn where we put the elements of the domain from our relation up here in one oval, and the elements of the range, those are the y's, in the other oval. And then we draw a line from the x of the ordered pair to the y. So -3 goes to 1. So that's what a mapping is. Now looking at this mapping, is this a function? Does each element of the domain go to exactly one element of the range? Yes. And more than that, each element of the range goes to exactly one element of the domain, which means it is a one-to-one function. Now, let's look at this second set here. Here's our relation. This is our domain and our range. Is this a function? Does each x go to one y, only one y? Yes, it is a function. Each domain goes to exactly one member of the range. So, you might be saying, well, what about 5? 5 is a member of the range. So, as long as the x only goes to 1, it's okay. What about this one then? There's our relation, our domain, and our range. Is it a function? Does each x go to exactly one y? No. Look at number 3, -3. -3 goes to 0 and 6, so it's not a function. All right. Now another example. Here's our relation. Let's figure out what is the domain and what is the range, and then state whether the relation is a function. So, what is our domain? Our domain is all of the x's. So, it's 4, 9, negative 9. And yes, I know there are two 4s, but we don't have to put it in there more than once. Then what's our range? If our domain is the x's, what's our range? Yes, our range is all of our y's. -2, 2, -3, 3 in curly brackets. Now, is this a function? I know we have a lot of visual learners, so let's look at this visually. We got two circles, ovals. One's the domain, the other's a range. Those are our domain, and this is our range. Now let's draw some arrows. Well, we have 4 goes to -2, 4 goes to 2, 9 to -3, -9 to 3. Is it a function? Does each x go to exactly one y? No. 4 goes to -2 and 2. Not a function. Okay, then we have the vertical line test. If a vertical line intersects a graph in more than one point, then the graph is not the graph of a function. This is my favorite test in all of math. I think I need to clarify, though, that when it says a vertical line intersects a graph, I mean a curve. So this one here and this one here, a curve, not just the graph. So let's try this. A vertical line, remember, is up and down, so we can use our pencil or our finger. Does that go across more than one point at a time? No, each one of these points by itself. Now let's look at this graph number 2. Oh, yes, that is a function. Now let's look at graph number 2 here. Here comes the pencil. Is it touching more than 2 places on the curve at the same time? Yes, it touches here and here. So is this a function? No. And then here, you can feel free to draw some curves and see if a vertical line goes through and only touches once or more than once, and practice a little bit. Okay, the independent variable. In a function, the variable is usually an x, and that variable makes up the domain. This is the thing that doesn't depend on anything. It's happening whether we like it or not. Time is always an independent variable because we can't change time. We can't adjust the time. How about the dependent variable? That's the other variable in the function, usually a y, whose value depends on that x. How many donuts can I fry in an hour? An hour would be the x value. The number of donuts that would be fried in that hour would be the y value. Functional notation are equations that represent functions. And the equation y equals 2x plus 1 can be written as f of x equals 2x plus 1. That this f of x replaces the y. And I know there tends to be a lot of panic about that. Like, what are we supposed to do between f and that value? Nothing at all. F is the name of the function. We could name this function Marissa. This is Marissa that takes the variable x as an independent variable. Or we could call it George. But Marissa and George are long to write, so we're just calling this f. The function f with the variable x is 2x plus 1. And we say that as f of x, and it's interpreted as the value of the function f at x. So, how do we do these? Well, here's our function f, and given that f of x equals x squared plus 2, we're going to find some values for f. We have put -3 in for the x variable here, so we're putting -3 in for the x variable here. When you do this, it's an excellent idea to put parentheses around what you're putting in for x, like this, because without the parentheses, your calculator will give you -9, because your calculator sees this as -1 times 3. So put the parentheses around whatever value you're putting for x. And then it's just a matter of a little bit of calculator usage or maybe some simple math knowledge. Negative 3 squared is 9. 9 plus 2 is 11. 11 is your final answer. Now, with these, you can also have variables go in. So with part B here, we're looking at the function f, and we're putting 3z in for x. So it's 3z squared plus 2. When you have a number touching a parenthesis, we distribute. So this becomes 3 squared z squared. 3 squared is 9. So 9z squared plus 2. We cannot combine any like terms because there aren't any, and that's just our answer. That's it for today. Have a great day. Be well.